In a world, in a university, 7 students tasked with making a project.
Basically, the car following system is like a mass spring system. It's just with proximity sensors, so it's perfect for our module.
We could do active noise cancellation, because that is innovative, it is useful for anyone, and it definitely involves modeling and a signal analysis.
But that's only going to use theory and programming. 2 nerds can do this.
Guys, how about a drone?
Hey!
Okay, but how does a drone work?
We can control the voltage over the motors, which causes a higher thrust from the rotors. Gravity pulls the drone down, and the motors have to counteract this to keep the drone floating mid-air. The height control system takes care of that. Tilting the drone allows controlling its horizontal position. The forces from the rotors are made unequal to tilt the drone, which accelerates it sidewards. The rotors are a distance r from the center. The real system follows these 2 relations. They were applied in the simulations to fine-tune the control system without having to start the drone. The equations were also linearized to make the calculations more efficient, so the drone can only correct small displacements at a time.
Here you can see the setup of our drone. It consists of 2 sensoring parts. This is our accelerometer part, which feeds information to our Arduino, including our optical sensoring part here. This Arduino processes information and gives 4 different PWM signals into our 4 ESCs. These 4 ESCs convert this information with the input from our motors with our battery into 4 different voltages to our 4 motors. Here we have our throttle controller, kill switch, and even an LED that gives information over the kill switch.
And this is our video. What do you think?
Okay, this is possible, but not in a week and a half.
Unfortunately, we have to conclude that the drone does not lift up yet. The PID system is working, but all system components coming together does not work yet by the time making this video.
The voltage input to the motor is not directly proportional to its angular velocity, as the motor has an internal impedance. This impedance is negligible, so the force can be modeled as a function of the voltage. That relation is not linear, so we linearize it around the working point, which shows the working point so that the motor's thrust cancels out gravity. This thrust is evenly spread out over the motors. Changing the angle is accomplished by producing a net torque. A drone with inertia J, angle theta, and motors at radius r changes the angle according to the following relation, where 2rFA is the net torque. The position change is then caused by the horizontal component of the force that balances gravity. Sin theta is theta in the small angle approximation. Here the masses cancel out, so the acceleration can be approximated as g theta. The small angle approximation limits our drone to small displacements, where it doesn't change its angle further than 0.5 radians. The height control system uses a PID control reacting to the difference between the wanted and actual position. This PID control outputs a voltage to go to all motors. The transfer function h of s turns that into a position in the simulation. The horizontal position control utilizes 2 PID controls. One takes the angle as an input and tries to keep the drone parallel to the ground. The second PID outputs a voltage taking the distance from the desired position as its input. In praxis, The position PID caused the drone to tilt in the first place, and as the drone's distance from the desired position decreases, the angle control tries to compensate for the angle. It overshoots trying to do so. This overshoot was tuned to decelerate the drone so that it stops when it arrives at the desired position.